So first in our unit on polar graphs, we're going to kind of review some of the stuff that you should have learned in pre-calculus so that you have a basic understanding of polar graphs and polar coordinates and all of that. And then later we'll go on and we'll see how calculus relates. So in math class, we usually use the Cartesian plane. Another word for it is rectangular. And these are points that are in terms of x and y. And it's beneficial to use in some contexts where you're talking about things that go left and right and up and down. But polar coordinates are used in other contexts, maybe like navigation, when you're talking about things in relationship to north, or perhaps modeling gravitational fields where you have like some sort of center of something. And so when we do that, we have a different type of axis. Here you can see that these, instead of left, right, and up and down, you have radiuses, radii, I guess, and then angles based off of that. So the polar axis is what we think of as the positive x-axis. So this part right here is the polar axis. And the center of the graph is called the pole. So this right here is the pole, and we've always thought of that as the origin. And then polar points are written as r and theta. And so if this is the point that I'm talking about right here, this would be my angle. So I start at the positive x-axis, so I'm starting in standard position to measure my angle. And then this part right here would be the radius. All right, so in rectangular form, we typically go left or right first, and then we go up or down, and that's how we draw our points. In polar form, we kind of go backwards. So we look at the angle first, and we locate that angle, and then we consider the r value. If the r value is positive, then we go towards that angle. So this right here would be an angle of pi thirds. And so we would say this is 1, 2, 3, 4. This is 5, comma, pi thirds. So if we had an angle that said -5 and then pi thirds, or a point, I guess, that said -5, comma, pi thirds, then we'd locate pi thirds, but instead of counting towards it, we would count 5 away from it, and we would plot the point over here, right? So if the r value is positive, you plot the point toward the angle. If the r value is negative, you plot the point away from that angle. One note that makes polar coordinates a little bit interesting in comparison to rectangular coordinates is that there are infinitely many ways to write every single polar coordinate. And the reason for that is because we have the positive r and the negative r, right? So we can say the same point but do a positive versus a negative value. And then also we have coterminal angles where we can think of this would be pi thirds, but it would also be 7 pi thirds. So we have all those coterminal angles, or we could say that's -5 pi thirds. So we always have infinitely many ways to write every single coordinate. So here, if I want to find some of those other ways, then in my calculator, I'm just going to find the angles that are coterminal to this. So if I have pi fourths, then I can add 2. 9 pi fourths would be another one. Or we could say 17 pi fourths. Or I could go back and I could think of pi fourths again. And I could subtract 2 and get -7 fourths. Or I could subtract 2 again and say -15 fourths. So all of these, if I were to graph them, they would be in the exact same spot as this point. And so that's some of the infinitely many ways to write a point. So here's our formula if we want to think about how to write some of these other points. If I keep the r value the same, then I'm just going to take the angle and I can add or subtract 2 pi to find those coterminal angles. All right, now, if I want to take the point and I want to use a negative radius to give me the same sort of answer, then if I think about it on here, I'm going to go ahead and do this in red so you guys can see it. Pi fourths is right here, so if I do 2 towards that, this is the point that we were talking about. So if I have a negative radius, then that means I want to talk about the angle over here, which is 5 pi fourths, so that I can say, hey, look at 5 pi fourths, but instead of going towards 5 pi fourths, you should do a negative radius and go away from it. So this point, if I'm writing the first version, I could say -2, and then I could say 5 pi fourths, right? So the way I think of it is the -2 bounced it to the wrong side of the circle, and adding pi to my original point bounced it back, if that makes sense. Or I guess I could say I added pi and bounced it to the wrong side of the circle, and then the negative r bounced it back. So I kind of think of it as like a double negative makes a positive, if that's helpful. So over here, the formula for this is if I change the sign of my r, then to my angle, I need to add or subtract 1 pi. It doesn't matter if you add or subtract, it has the same effect of moving it to the opposite side of the circle. And then after that, I can go ahead and find angles that are coterminal. So now I can go ahead and take 5 fourths and add or subtract 2. So I could say +2, so 13 pi fourths, 21 pi fourths, -3 pi fourths, okay, so as you can see, infinitely many ways, and all of these would plot that exact same point. Okay, so one of the things that we need to be able to do with polar coordinates and rectangular coordinates, just like we learned last unit when we were talking about parametric equations, is we want to be able to convert back and forth between polar and rectangular, whether that be a point or an equation. So before we do that, we have to know how the conversions work. And they're kind of based on the same thing that your unit circle is based on. So if we have this is the angle that we're talking about, this would be like the radius of this point that would end up on the unit circle. This part right here would represent the x-coordinate of that point. This part right here would represent the y-coordinate of that point. So if I think of angles and SOHCAHTOA and how things are related to that theta, I would say that cos theta is adjacent over hypotenuse, and sine theta is opposite over hypotenuse. And so if I want to isolate the x and isolate the y, I would just multiply the r to the other side. So my first conversion formula is that x equals r cos theta, and my second is that y equals r sine theta. Okay, so if I have the polar point 2 pi fourths and I want to convert it into rectangular, then I just need to plug in the r and the theta for these formulas. So x equals r times cos theta, and that's 2 times root 2 over 2. And so the x-coordinate of the point would be the square root of 2. And then y equals r sine theta. And so that's 2 times the square root of 2 over 2. And so the y-coordinate is square root 2. So that means that if we have the polar coordinate 2 pi fourths, the rectangular coordinate would be root 2 root 2. Okay. We also need to be able to take something from rectangular form and convert it into polar form, so we're going to draw the same picture, but we're going to get different information from it. So here, if I want to convert this into polar, then I'm going to say x squared plus y squared equals r squared. So if I wanted to isolate the r, I would just need to square root. Now here we don't have to put plus minus the square root because the positive r's and the negative r's in the equations end up not making much of a difference because of the symmetries of the graphs, I think. But either way, we don't have to put the plus minus. It's appropriate here just to use the positive version. All right, and then we also have tan theta equals y divided by x. And so if I wanted to isolate theta, then I could say theta is tan inverse of y divided by x. Now, typically when we see something that looks like this, we think of it as an inverse function. And with tan inverse, a tan inverse function can only have answers in the first quadrant or the fourth quadrant. But this is not a function because we are the ones who did the tan inverse. So when you're looking at this, it is appropriate to find angles in all four quadrants depending on the problem. So that's something to keep in mind. All right, so if we look at this problem, it says to convert the point 2, -2 into polar form. And whenever you do a rectangular coordinate into polar form, you want to be careful about which quadrant the answer's in so that when you find the angle, you find the angle that's in the correct quadrant. So this point is right 2 and down 2. So that means we're going to make sure that our answer is in quadrant 4 when we find the information. So we're going to do, we'll go ahead and find the radius first. So I have r equals 2 squared plus -2 squared. And so that's the square root of 4 plus 4, which is the square root of 8. And then theta is going to be tan inverse of -2 divided by 2. And that is tan inverse of -1. So we would want to look at our unit circle and look to where the y-coordinate divided by the x-coordinate simplifies to be a -1. And that happens in 2 spots. It happens in the second quadrant and the fourth quadrant, so that's where we're going to look. And that would happen at 7 pi fourths. So I'm going to say that my theta is 7 pi fourths. So this would be square root 8, 7 pi fourths. All right. Now to go back to this idea of should we use the positive or negative r value, you could say that this is negative square root 8, and then you would use the second quadrant angle to make sure that it would bounce it back. So we're typically going to just use the positive version, but if you wanted to think of that as a plus minus, mathematically speaking, for this unit, you definitely could. Okay? When we start talking about polar equations, and we are converting things back and forth with polar equations and rectangular equations, we always want to make substitutions using our little formulas that I showed you. So that's the r equals square root of x squared plus y squared, and all of that. Our goal is to continue simplifying after we make the substitution until we have a recognizable equation. Okay, so underline that simplify until you have a recognizable equation. Because we are used to rectangular problems, it's going to be a little bit easier for us to start with polar and convert it into rectangular because we'll know when we're done. We'll recognize it and then we'll know that we're finished. It's a little bit more difficult to start in rectangular and convert to polar because we're not as used to those equations. So what I've done here is I've given you a list of what should be recognizable polar equations so that you guys can see them, and when you're converting you can have a goal to work towards. So the first type is equations that are straight lines. So if you notice looking at this whole thing right here is that almost all of the polar equations are in the form r equals, so that's going to be typical for us. One of the 2 exceptions is this right here, and this is a straight line where the y-intercept is the origin. Okay, so I'm going to say y-intercept is the origin. And so that means these are straight lines where maybe it's a completely vertical line, maybe it's a completely horizontal line, or maybe it has a y-intercept that's just not in the middle of the graph. These all represent circles. If we have r equals a number, then that means that the center of the circle is the origin. And then these are just what they look like if your center is not the origin. Next, we have conics. These graphs are all conics. So when the two numbers are the same size, then you have a parabola. When the first number is bigger than the second, you have a hyperbola. And when the first number is, did I say bigger than the second, smaller than the second? When the first number is bigger than the second, we have an ellipse. I'm not saying that so that you have to memorize those at all. This is just something that we typically look at in pre-calc, and you guys, we work with them, we see exactly why each one is what it is and how it works, and so I'm just trying to jog your memory from that. Just kind of informational, not to be memorized. All right, and then the last is, I call these special polar graphs, but don't Google that because that's probably not what it's called online. And these are graphs that we only really talk about in terms of like polar form. We don't convert them into rectangular form, we just talk about them in polar form, and they have special names. So I was supposed to put this in your packet, and I forgot. So do not sketch this, I will give you a scan of this tomorrow. But these are all the different polar graphs that are special. So the first one on your list is a cardioid. It's kind of heart-shaped, which is why it's called a cardioid. The next two are both, I call it limacon, but I think it's limason. There's some sort of funky accent there that makes it sound different. So we have one with an inner loop, and then this is the one we typically think of without the inner loop. They're just getting a little bit more specific here. Yeah, so this is a limacon or a limason or whatever, and this is the one with a loop. And then this is a rose, so these are all the different roses. We'll talk more about those when we get to a point where we need to. And then the other formula that's unique is this one, because there's an r squared. So all of these were in terms of just r equals something, except for a straight line that goes through the origin, and then this graph right here, which is called a lemniscate. And a lemniscate looks like a perfect infinity sign. So those are these two. All right, so I will give you a copy of that when I see you guys tomorrow. Okay, so on this side of the page, we're just going to go ahead and convert some equations, and this part is not too bad. So I'm going to go ahead and write down those conversion formulas so that I can refer to them. All right, so for these two, I like to remember that r squared is x squared plus y squared, just because sometimes you'll have the r alone and sometimes you won't, so it's kind of helpful to have both of those. So here we have an r that's alone, and you have two options. You can work with the r, or you can go ahead and square each side, and it doesn't really matter which one you do. So I'm going to go ahead and just square each side. So we have r squared equals 4. And so instead of writing r squared, I'm going to say x squared plus y squared equals 4. And so this is a recognizable equation. It's a circle centered at 0, 0 with a radius of 2. All right, here, this theta equals, so I know this is a straight line that goes through the origin. So theta is tan inverse of y over x. So I'm going to write tan inverse of y over x equals pi thirds. And then to convert it into a rectangular equation, I've made the conversion already, but I want it to be simplified until it's a recognizable form. And so I'm going to go ahead and do tan of each side, because in rectangular we like for the y to be isolated. So I'm going to have y over x equals tan of pi thirds, which is square root of 3. And then I want the y alone, so I'm going to multiply the x to the other side. So this is a linear equation, y equals square root 3x plus 0, so it has that y-intercept of 0, and the slope would be root 3 over 1. All right, for this one, I'm going to go ahead and convert secant as 1 over cos. And the reason I'm going to do that is because I want to see if this sort of thing is going to happen, or if I need to square things to make it an r squared, so that I can use this replacement or substitution. So I'm going to go ahead and multiply the cos to the other side. R cos theta equals 1. And so r cos theta is x. This is x equals 1. And so that's the equation of a vertical line. This one is going to be a little bit different because the r, even if I divide the cos to move it over to the same side with the r, it's not going to be r times cos theta. And so for this problem, I'm going to go ahead and multiply each side by r. The reason I'm doing that is because that's going to make this r squared, which I know how to work with. And that's going to make this 3r cos theta, which I know how to work with. So this is r squared equals 3r cos theta. So we have x squared plus y squared equals 3x. So if you can recognize what this is going to give you, this would be a circle. This means it's not going to be centered at 0. So technically this is a recognizable equation. This would just be like the standard form of it, or I guess I should minus that over and make it equal 0. So we can go ahead and say x squared minus 3x plus y squared equals 0. There's our standard form. Or I guess that's actually called the general conic form of a circle. The standard form of the circle would be this. Sorry, I misspoke. So if we wanted to get that into the standard form so we could see where the center is and what the radius is, then we have to do the process for completing the square. So we would do -3 divided by 2, which is -3/2, and then we would square it. And so that's 9 over 4. So we would add 9 over 4 right here and add 9 over 4 right there. And that would give us x minus 3 over 2 squared plus y squared equals 9/4. So there's our general conic form. There's our standard form. So both of those are recognizable. They're both circles. All right, so then to go backwards, converting from rectangular form to polar form, here we could say this is r squared equals 16. And then if we're thinking about our list of recognizable polar equations, we know that typically that r needs to be by itself. And so I'm going to go ahead and square root to each side. R equals 4. So that's recognizable as a circle. So our circles, r equals 4, recognizable. Over here we have y equals 8, so I'm going to replace the y with r sine theta. And then again, I'm going to isolate the r, so r equals 8 over sine theta. Or you could say r equals 8 cosecant theta. Two different ways, just thinking about what we know about trig identities. So both of those are good. All right, so we'll talk about this more in class when it comes up within the context of the class, but as far as the special polar graphs, so those ones that I showed you guys the pictures of, not these ones right here, you're going to need to be able to look at the graph and see the shape and say its name. You're going to need to be able to classify it. You're going to need to be able to look at the equation of a rose and know how many petals it has. We'll talk about that in class. And you'll need to know what interval to use to trace out the entire curve once. So is it 0 to pi, is it 0 to 2 pi, whatever. So these are things that we'll talk about in class, but these are the parts of the special polar graphs that you're going to need to memorize, and I would recommend making flashcards for those. Not tonight, but over the course of the unit.